All right. Hello, everyone. Welcome to our workshop. And based on our time zone, I think good morning, good afternoon, good evening. This is the workshop for IEEE Intelligent Vehicle Symposium 2021. And the title of this workshop, as you can see from these slides, it's Cooperative Driving in Mixed Traffic. This is a part one of our workshop. There will be a part two tomorrow, which will be another 2.5 hours. As you can see from this picture, we are supposed to meet here in the beautiful city of Nagoya in Japan because that was original venue of that. But due to the pandemic, I think most of us we get used to attending meetings online. And to be honest, this is the third one that I have been held since pandemic, a workshop through online through Zoom. Which is a good thing as well because we are able to join meeting just by clicking one link. And I'm going to give another round of welcome from all we workshop organizers, including myself, Ziran Wang from Toyota, Dr. Guoyuan Wu from UC Riverside, Dr. Shuo Feng from University of Michigan, Dr. Zhaojian Li from Michigan State University, Dr. Jia Hu from Tongji University, and Dr. Meng Wang from TU Delft. If you have any question for us, please feel free to just send a private message in the Zoom channel or just send us an email. The goal of this workshop is to discuss progress and challenges in developing intelligent vehicle technologies in the mixed autonomy traffic environment. So the key thing that we're going to talk about is the mixed autonomy traffic, where our environment has, part of the vehicles are autonomous vehicles or connected automated vehicles, but maybe the majority of the vehicles they are still human-driven vehicles. How do we study the interactions among those different types of vehicles? That will be a very challenging research question to be solved in the near future. These are the workshop speakers from today's session, or actually it's another way around. This is correct. Dr. Zhang Bosun from Southwest Jiaotong University, Dr. Surrogate Avatsov from Toyota North America, Dr. Ben Yougang Bian from Hunan University, Xishun Liao, Badak Chalaki, Haoran Wang, Yimin Zhang, and Yong Wang. Some of them, they contributed papers to our workshop. Some of them, they are invited speakers to our workshop. And some of them, they will give a lightning talk, which will be just 5 to 10 minutes from a high level to introduce their work. And this is scheduled for today's session. We will have 2 full talks at first from Dr. Sun and Dr. Wang, Mr. Wang. And we will have 3 lightning talks. As I said, each of them will take 5 to 10 minutes. And after that, there will be another 3 full talks. Some instructions for this workshop: please kindly mute yourself if you're not presenting. And if you have any question, please feel free to ask in the chat box with the format tag someone or add someone. For example, if you want to ask me a question, you can add Ziran, which is my name. What is the penetration rate of connected vehicles in the system? So in this way, the recipient of your question will be easier to locate your question and to answer your questions. And always feel free to follow our websites for future updates about like the recordings of this workshop, the slides of different talks, call for proposals or call for papers for future workshop, conference, or special issue. Just stay tuned with our workshop website as well as our committee website, because this workshop is also organized by our IEEE ITS committee in Internet of Things in Intelligent Transportation Systems. And if you have any question, please feel free to send me an email. Just a preview of tomorrow's session. This will be tomorrow again for our part 2. We have speakers lining up from universities, from industry, which is very interesting as well. And this is tomorrow's session. We'll also have 2 full talks, 3 lightning talks, and another 2 full talks at the end. Okay, so without further ado, let's start our first session today. Dr. Zhang Bosun. Dr. Sun, can you hear me?
Yeah, I think so. Yeah.
Great. You can start to share your screen, and I can do a brief introduction.
Okay. All right.
Stop share. Okay. So Dr. Zhang Bosun is currently a professor and associate dean in the School of Transportation and Logistics at Southwest Jiao Tong University in China. He received his PhD degree in transportation engineering from RPI in the United States in 2014. And before that, he received his bachelor degree in civil engineering from Tsinghua University in China in 2009. His current research interests are collaborative decision working for mixed traffic with connected automated vehicles and human operated vehicles. Now, Dr. Sun, the stage is yours.
Okay. Thank you, Saran, for the introduction. So I guess I have 30 minutes or 20 minutes for
20 to 25 minutes for a presentation, and another 5 to 10 minutes for discussion.
Okay, good. Just want to make sure. Good morning for friends in Asia, and good afternoon. Also for our U.S. friends, and also, we may have other friends from the globe. So today I'm going to talk about cooperative ramp merging for mixed traffic. So here I want to present a couple papers related to this topic. Okay, so here is a brief outline. I'm first going to talk about using this ramp merging example, talk about cooperative decision making for mixed traffic, basically. And then I'm going to talk about hybrid, centralized, decentralized control, and closed loop control, just for better, capturing this problem, and also some, implications for real-time computations. And also, I'm going to talk about a macroscopic right-of-way trading mechanism, which is, sort of similar to the for example, this tradable, road tickets, but in a different version. And then I'm going to touch a little bit on the car following heterogeneities and how to do short-term trajectory prediction, followed by some technical level, trajectory planning and tracking. Okay. So first, let's look at this this traffic conflict problem. So basically, ramp merging, intersection control, these can be, these are traffic conflict, and this is the most fundamental problem in transportation science and engineering. So at least in theory, with the help of connected automated vehicle technology, we think it's possible to mitigate or eliminate traffic conflicts, also in the mixed traffic environment. Okay. So I personally call this, so my group called this problem cooperative decision making, and of course it's also related to control. Okay, I personally call that a CDMMT. That's cooperative decision making for mixed traffic. Okay, so that's the background of this problem. I presume most of us, know this well because we are from the same field. We're talking about this different level automation for connected automated vehicle and different level of connectivity. So in the academia, people are focusing, there are different focus from the industry field and academia. From my perspective, we focus on the problem with higher level of connectivity and also automation. So that's background. So I'll be keep tracking some of the news related to connected automated vehicles. So most of us, know these news or problems well. So there are some key challenges, including the technical difficulties, for example, hardware, sensing technologies, communication, and also mixed traffic really makes the problem much more difficult because now we have people involved, and we know humans are myopic, stochastic, and usually non-cooperative. So which really makes the problem very difficult. And also, the key message I want to convey here is, from the system perspective, we really want the system to be efficient. By saying cooperative, we really want the system to be improving, because cooperation is not necessarily system improving. In some cases, for example, in this ramp merging scenario, well, we have a ramp vehicle who try to merge on the main line, but to ensure this this merge activity, we may want the a platoon of vehicle on the main line to slow down. And that case is not necessarily system improving. So what I want to say here is to design efficient control technologies or decision-making strategies in mixed traffic environment, we really need to pay attention to the system efficient problem. Okay, and of course there is also the so-called ethical dilemma, because sometimes we may have if a vehicle cannot be stopped, it has to hit either a puppy or a group of people. In this case, it may be a simple choice because most people would choose to hit this puppy because that's comparably less impact. But what if, well, I can give a bunch of other scenarios in which that the choice is not so obvious. So there are some ethical problems we have to deal with. Okay. So now to start our discussion. So basically we are looking at, to narrow down the topic a little bit, we are looking at the merge section with a bunch of human operated vehicle and a bunch of connected automated vehicles. So in this ramp merging scenario, we think this problem can be modeled by a bi-level programming framework. So in the upper level, it's essentially a merge sequencing problem, in which the CAV try to seek appropriate gaps on the main line to fulfill the merge maneuver. And the lower level problem is essentially a trajectory design problem. That's how to design the trajectories. Okay, so essentially that's a bi-level optimization framework. So if you so basically the upper level, that's the merge sequencing. So let's look at this problem. So if you know this problem well, it's essentially equivalent to, we have a couple of gaps on the main line, and we try to decide which gap for a target vehicle to merge. Okay. So essentially this problem can be very well addressed using the dynamic programming framework. So that's some dynamic programming formulations, but I don't want to talk too much on the mathematical details. And also in the mixed traffic environment, the harder part is we need to capture all possible scenarios that can potentially occur in the mixed traffic scenarios. In this case, we categorize basically 13 scenarios in which, in the mixed traffic environment that can possibly occur. So with respect to the mainline leader, the mainline follower, and the target vehicle, which is the ramp vehicle, and the vehicle could be autonomous vehicle, which is represented by A, could be human operated vehicle, that's represented by H here. And also some case, there are only 2 vehicles involved in each merge maneuver. And in that case, we have a placeholder N here, that's for scenario 8 up to scenario 13. So that 13 scenarios should capture, all possible cases that can, appear in this context, car-folding context. And also with respect to, the reason why a ramp vehicle, let's say vehicle 2, cannot easily merge onto the main line, there are also some possible scenarios. For example, this could be, this ramp car is too close to the mainline vehicle, or too close to the mainline follower. So there are essentially different reasons that prohibit smooth merging for this problem. So we need to explicitly consider all that scenarios. So with that, the lower level problem is essentially a trajectory design problem. In this case, we are looking at multiple vehicles involved. Could be 3 or could be 2 to 3 vehicles involved in each lower level problem. So in this case, we are also formulating this using a DP type of approach. So that's the harder part is essentially the model of the final state constraints, which is related to the lateral dynamics. But in this work, we didn't really consider very complex, very detailed lateral control here. So so that's for, we have 3 vehicles involved. Vehicle K, that's the ramp vehicle. Vehicle K lead is the mainline leader. Vehicle K follow is the mainline follower. So we basically consider for all these scenarios, in which scenarios the vehicle K could be non-cooperative, could be controlled, could be faster, slower, and undetermined. We list all these possible options. Okay. So the lateral dynamics here is very it's rather it could be a complicated problem, but here we consider is a discrete choice like literal ramp merging decision. Okay, it's a lane change or merge. Okay, and for the longitudinal dynamics, we tried basically different car-folding models, including some of the well-known Gibbs model, IDM, EIDM, and also there are some other intelligent driving car-folding models, such as deep learning-based methods. So that's in generic form, it can be written in this UMEC formulation. Okay. To skip most of the mathematical details, let's directly come to the results. So here we show basically the speed, time speed profile, and also the acceleration, deceleration profile. We show that the cooperative case is, in this case, is much better compared to non-cooperative scenarios, and also in terms of the speed contour, which also shows that the cooperative case is much better. So if we look at the fundamental diagrams at different penetration, it shows that, of course, with the increase of CV penetration, the problem is much better. And also we show that the CDMMT can further improve the capacity by about 10% to 15%. So that's for the first one. For these, the following papers, I only want to talk about these in very brief, because I think I really had limited time. So in the first work, so basically it's a deterministic scenario. As I said, the difficulty is really the system stochasticity, and that this is not quite considered in the first work. And also the computational problem, the computational efficiency is also a problem, because eventually we are looking at some real-time, control or real-time application. So the solution to this is we look at the closed loop control, in this case, a modal predictive control, and also to ensure computational efficiency, we basically propose a so-called hybrid centralized decentralized system, because the previous work is mainly centralized. Here we propose a hybrid system that we show it can basically solve this problem faster. And also for the lower level problem, it's an NP-hard problem. Here we use a computationally efficient solution approach for to solve this lower level trajectory design problem. Okay. So let me skip. So the idea here is we use some hybrid control. We have a centralized controller and a bunch of OBU that's on each autonomous vehicle, and we have the centralized control solve the sequencing problem and then pass the lower level computational tasks to each OBU on the smart vehicles. And the smart vehicles basically solve the lower level problem and then return the problem to return the solution to the upper level. And the upper level can, in this case, as you can tell, it's a hybrid approach that can basically take advantage of the computational power for each smart vehicle. Okay. So let me skip this. Directly come to the results. So basically, we use hybrid control. We show that, and also we test this closed loop MPC framework. We show that the MPC approach is more robust compared to open loop control, and also is much better compared to non-cooperative scenario. Okay. And in terms of time, because here the time is mainly the main concern, we show that this hybrid system, centralized decentralized control, can significantly reduce the computational time. So for each computation, for each task, we show the computational time using hybrid control is, if you use correct method, it's on the milliseconds level. In most cases, 40 milliseconds, which is, potentially that implies this method can be used for real-time application. Okay. Briefly mention we are very excited about this concept. Is called microscopic right-of-way trading. Essentially, we in the previous work, we usually assume that the CAVs can be designed to be cooperative, but of course this conflicts the self-interest nature of human. So in this case, we basically assume the vehicles can be categorized into cooperative vehicle and non-cooperative vehicle. So we believe that both CAVs and HVs can behave cooperatively if enough incentive can be provided. Otherwise, if there's no incentive, it's not safe to assume that the CAVs can behave cooperatively. So this mechanism is called microscopic right-of-way trading. Okay. So essentially, we are talking about right-of-way trading in this mixed traffic. We are talking about microscopic level rather than the tradable road tickets like these in the field of traffic management. Also, it's a game theoretical approach. We need to address the trade-off between individual rationality and system efficiency. And also, we want to design the problem for incentive compatibility. Okay, so here that's the strategy, the dominant strategy, incentive compatibility. That strategy, that's the one we used. Okay, that can guarantee basically MV minimization. Okay. These are just some brief definitions. So we assume that the ramp vehicle could be a payer, basically offer money to the ramp follower who's going to, behave cooperatively, and the receiver is essentially the ramp, could be the mainline follower who's going to behave cooperatively. Okay, and there are a couple of rules we tested. For example, equal allocation, that's basically allocate that the total revenue equally among these two participants. And also there are a bunch of other rules. Some of the rules are more advanced in the sense it can, it can basically minimize the envy. Okay. So that's some results we show. let's assume the value of time is 80, that's Chinese yuan, RMB per hour. The fuel cost is 7 RMB per liter. And after applying that microscopic right-of-way trading on congested ramps, we found that the direct cost saving is around 80 to 100 Chinese yuan per hour per session. And because I'm in Chengdu, Sichuan, China, so if we apply this case to 47 merged sections of the second ring road of Chengdu, we do some simple computation. It's found that the direct cost saving is around 7 million Chinese yuan per year. So that's a good amount of saving, right? I think I still have a little of time, but let me just quickly go through. So that modern car following heterogeneity is for better short time trajectory prediction. So let me just quickly scan through these things. So basically we come up with a framework, a statistical modeling based framework then can be used to better describe the heterogeneity of human driving behaviors in macroscopic sense. So let me just quickly scan through this part. And also for short-term trajectory prediction, this is really a hot field because people are talking about using a deep learning method for trajectory, planning, trajectory prediction. And in the aforementioned tasks, for example, these cooperative decision-making tasks, that relies basically rely on the accurate estimate prediction of trajectory in short term. So in this case, the predicted trajectory serves as the key input to our previous problems. So in this case, we use a graphic representation learning method combined with the LSTM for short-term trajectory prediction. So the key here is the graphic-based representation learning can better capture the spatial interactions between the vehicles on the road. So that's more intuitive compared to the black box, the black box like deep learning techniques. Okay. So let me quickly scan through this part. Some of the results we compare to a few benchmarks. That's the state of the practice from some of the literature. So it shows like our graphic-based learning method is fairly efficient. Quickly scan through this part. And so for all these 5 topics that I mentioned before is mainly on the decision-making level. So the last part is essentially the trajectory planning and tracking. That's more like the technical level. But I think since I'm running out of time, I'd rather skip that part. Because I want to leave more questions for more time for questions. So the future directions, it may be some integration of trajectory planning and trajectory tracking, considering trajectory replanning. And also essentially we're talking about some time delay systems if we want to really implement this in real time. So that time delay problem had to be considered. And also there are some challenges in the microscopic right-of-way trading, and also the stochasticity in the problem need to be better encapsulated. And also we want to generalize this problem to other scenarios, including intersections and so on and so forth. And also road test experiment, because the above discussions are mainly based on simulation and numerical results. Okay. Here is a bunch of papers we are working on or published. I want to thank our group members at Southwest Jiaotong University and our key lab collaborators, Guoyuan Wu from UC Riverside and Ray Ma from the University of Alabama in Huntsville. And this bunch of work are supported by the Chinese NSF and Department of Science and Technologies in Sichuan, and also special thanks to Geely Automotive who sponsored this part of this work. Okay, I'm open to questions or discussions.
Thank you a lot, Dr. Sun. I think we have right now we have at least 3 questions in the chat box, and I will raise those questions for you. The first question comes from Jia Hu, and I think he asked, what's the difference when you mention closed loop and hybrid?
These are two different concepts. The closed loop is with respect to the open loop control and closed loop control. So basically in closed loop we have real-time feedbacks. So every time the vehicles in the system update their states, we have real-time feedbacks from these vehicles, and that information can be utilized in closed loop control. But for open loop, basically we assume there's no feedback in the process. So we assume there are perfectly as predicted. But in the real scenario, it may not be the case. And open loop sometimes it lead to fail to merge. So for the merging problem. And hybrid control, it's essentially with respect to the way the vehicles are controlled and the way the computational tasks are conducted. So in literature, we are more familiar with the centralized control and or decentralized control. So centralized control is system efficient, but the computational time, may be a problem. So decentralized control cannot guarantee system efficiency. So as you can see, there are problems with centralized control and decentralized control. So in that work, we basically propose a so-called hybrid control that can basically take advantage of centralized control and decentralized control. So in short, there are 2 main contributions in that work. One is to use closed loop control, the other is to use hybrid control. So
hi Zhenbo, this is Jia. Sorry to jump in.
Yeah.
I guess my question originally I was trying to find the distinct difference between your first research and the second research. I kind of feel like the first research is closed loop as well, but then it kind of comes to me then, is it the hybrid thing you were mentioned about that really takes in the closed loop design? It's very hard to ask this question, but the key is what's the difference between the first and second? Why the second stands out so much?
The first one is more like a conceptual, or methodological work that basically we propose this bi-level modeling approach for this random merging problem. So the short answer, the first work is essentially open loop. So, and also it didn't quite consider the stochasticity in the problem. Therefore, meaning the trajectories of the vehicles in the system can be predicted perfectly. So that's mainly a limitation of the first work. So in the second work,
so you don't have a run back to the upper level.
No, in the first work,
no. It does. Okay. I see. Okay.
Yeah.
Cool. All right. Thank you.
Thank you.
Thank you, Jia, and thank you, Dr. Sun. The second question and the fourth question a little bit related, so I'll ask them together. The second question is, how far into the future do you need to predict? I think that's for trajectory prediction. And the fourth question is, for trajectory prediction, do you consider surrounding vehicles' behavior into your model? What kind of information are needed?
These are all very good questions. So for the first question, essentially we're looking at this merge maneuver activity, that process, process usually lasts for, let's say, 10 seconds to 20 seconds. That ranging from, the vehicle enter the upstream merge section, close to the merge section, and ending at the vehicle, leave the merge section. So that process usually lasts for 10 to 20 seconds. So the prediction should also last for, let's say, 10 to 20 seconds. That's basically what we meant by short-term trajectory prediction. So the second question, that's on, remind me the second question, Saran.
Sure. Do you consider surrounding vehicles' behavior into your model? And if
Oh, yeah,
so,
yeah.
what kind of
So
information?
the short answer is, yeah, we need to, we need to predict. We also need to predict how the surrounding vehicles are going to do in these scenarios. So essentially, by saying trajectory prediction, in this work, we are trying to predict basically every vehicle in the stream. So the short answer, yes, we need to predict. We need to have the surrounding, the information from the surrounding vehicle, and we need to predict that.
Thanks. And one last trivial question: will the slides be posted later? Because I see a lot of materials, and you don't have time to go through. Will
I can share the slides. I can share the
Great,
slides.
great. So yeah, we can share that directly with me, so I can post that on our website.
Okay.
Yeah, thank you.
Cool.
Thank you, Dr. Sun, for a very interesting topic.
Thank you for having me.
Thank you. Okay, so let's switch to our next presenter. Our next presenter will be Mr. Haoran Wang from Tongji University. Haoran, you're there, right? You can start.
Yeah, I'm here. Okay.
And Mr. Haoran Wang received he's currently a PhD candidate with College of Transportation Engineering at Tongji University in China. And previously he received the bachelor degree also from Tongji University in 2017. He's a researcher on vehicle engineering, majoring in vehicle control and cooperative automation. And this work he will be presenting, it's one of our workshop papers that he has done with his advisor, Dr. Jia Hu. Go ahead, Haoran.
Okay, thank you. Hello, everyone. This is Haoran Wang from Tongji University. I'm honored to present my paper, Mixed with Suchin a cooperative adaptive pulse control engine controller. At first, I want to make a brief intro about our group. I formed the group Cooperative Automated Transportation Lab. We name it CAT Lab. My advisor is Professor Jia Hu. We mainly make efforts on 5 topics. Topic 1, the vehicle control. We have developed several ADAS controllers, including ACC, adaptive cruise control, ALC, automated lane change, and AVP, automated valet parking. In addition, we have developed the path tracking and eco-driving controllers. The left video at the bottom of this slide records the field test of our path tracking controller. Turns, street cruising, and curve scenarios are included. The speed limit is 80 kilometers per hour. In all scenarios, tracking error is less than 12 centimeters. Topic 2 is vehicle cooperation. We focus on multi-vehicle system, especially CCC. We have promoted the field implementation of CCC. The video in the middle records the field test of our CCC controller. This CCC is human in the platoon. It means the leader is human-driven, and the followers are controlled to follow their front vehicles. As shown in the right video, another implementation is the container trap tuning. This system has been commercialized in Shanghai Yangshan Port. It leads to $0.2 billion economic benefits every year. Topic 3 is the controllability field test of level 3 autonomous vehicle. we consider human factors to quantify controllability in case of system failure. Topic 4 is mixed traffic. It includes dynamics modeling, speed harmonization, and signal coordination. Topic 5 is simulation platform. We have embedded vehicle dynamics model into traffic simulation and developed the traffic and vehicle integrated simulation platform. Okay, now I will give my presentation on CCC lane change. It covers the following aspects: motivation, methodology, and evaluation. At first, I want to give the motivation of my CCC lane change controller. You know, transportation is now facing 3 main challenges: mobility, safety, and sustainability. Traffic congestion problem is now increasingly serious all over around the world. Over 400 cities in 56 countries are now experiencing increasing level of traffic congestion. Because of traffic congestion, people spend more time against the free flow periods. Reports show that 5.5 billion hours and of the travel delay and $121 billion cost every year is caused by the traffic congestion in the US. Safety problem is also very severe. Reports show that over 3,700 traffic fatalities is caused in the US in 2017. Traffic crash has been the leading cause of the deaths for ages from 11 to 27. Here we list the main cause factors of crash. Most of the factors are driver related. As for the sustainability, road transportation leads to 2.9 billion gallons of wasted fuel and 56 billion pounds of additional carbon dioxide every year. In order to address these challenges, cooperation is given with great expectation. Cooperation among pedestrian, vehicle, and infrastructure could be achieved by portable smart devices, CVs, and intelligent transportation systems. As an important application of CV, CCC, cooperative adaptive cruise control, is now in rapid development. CCC is proposed by adopting V2S communication to the ACC. Conventional ACC could reduce driving load and improve driving experience. CCC is expected to bring more positive effects. Smaller headway will benefit the driving mobility. Equal portion technologies may achieve sustainability, and automatic control will reduce driving error and improve driving safety. However, you know, conventional CC is longitudinal only. By enabling CVs in platoon with lateral control, the CCC is now given with a new opportunity, CCC with lane change capability. Let's consider these scenarios. First, the scenario on the left, the dark blue vehicles are CVs in platoon. The white vehicles are surrounding human-driven vehicles. They are mixed in the traffic. It is very usual that there is a slow-moving HB in front of the platoon. In this scenario, a longitudinal only CCC would make great loss of mobility. The red figure illustrates another scenario. The dark blue CVs are in platoon, and they must change lane and run into the upper ramp. If the system is without lane change capability, the platoon has to be disengaged. This may break the control continuity. So we need to control CCC to change lane. Conventionally, the platoon is controlled to change lane simultaneously. This simultaneous platoon lane change process is illustrated in the left figure. From step 1 to step 5, all CVs in a platoon take same actions and change lane simultaneously. We name this method simultaneous platoon lane change, SIPLC. Now we consider the scenario aforementioned in the right figure. We assume a Perturb with 5 CVs. Falling headway in Perturb is 1 second, and the cruising speed is 30 meters per second. 5 multiplied by 1 and multiplied by 30 equals to 150. Therefore, the length of a Perturb in cruising is over 150 meters. It means 150 meters gap shall be found to make a lane change. This gap indicates 10.75 traffic density. It is the level of service A. We can see that in this case, the conventional simultaneous Perturb lane change method can only be applied in the traffic with level of service A. This greatly limits the implementation of Perturb lane change. So the conventional SLPLC method is with low change capability. In previous study, we have proposed a Perturb lane change controller, successive Perturb lane change, SLPLC. The left figure illustrates its typical application scenario. The dark blue vehicles are followers in Perturb. The light blue vehicle is the Perturb leader. The white vehicle is a front slow-moving HB, and the gray truck is a slow-moving truck. The gap between the left truck and the front HB is big enough for single vehicles to change lane. The Perturb is impeded by its surrounding slow-moving traffic. So in order to keep running mobility, the Perturb has to change lane. The Perturb, the leader change lane first, and all followers track its trajectory relative to the left slow-moving truck. The CVs in Perturb could then change lane successively. This SLPLC controller enhances the capability of Perturb lane change. However, there are still shortcomings. Let's see the scenario in the right figure. The SLPLC can't change lane if the left HV accelerates or the front vehicle decelerates, or there isn't enough space to settle down the Perturb. So the successive Perturb lane change is with low success rate. Considering these limitations, we propose a new CC lane change controller. This controller is capable of making space to change lane. At step 1, a gap should be selected if it is not for single vehicle's lane change. At step 2, the last CV change lane to the gap. At step 3, the last CV slows down to open the gap. At step 4, the gap is enough to hold one more vehicle, so the last but one CV change lane. Just like this, all CVs in Perturb could change lane into the gap in turns. This method ensures the lane change process won't be interrupted. It is nearly with 100% success rate. Applying this concept, we now propose a Perturb lane change controller. Its methodology is presented in this section. This figure shows the control framework. It consists of 3 modules. Module 1 is in charge of Perturb decision making. It decides the gap to be selected for the lane change, and the information of vehicles, including CVs and HVs, are passed to Module 2. Module 2 is the planning module. It plans trajectory by the proposed CC lane change controller. Module 3 receives the control command from Module 2 and activates the control commands. Applying this framework, we show the developer Perturb decision maker and a CC lane change controller. Since front CV should follow its rear CV to change lane, so a new information topology is proposed here. In this topology, information is passed from the rear CV to the adjacent front CV. A simple rule-based Perturb decision maker is proposed. It includes lane change decision making and desired speed decision making. A gap enough for CV lane change maneuver could be used for the Perturb lane change. And for the desired speed decision making, it follows a simple rule. The last CV change lane at a speed same with the rear HV. When the last CV finishes lane change, it should decelerate to open the gap. So the desired speed of the platoon should be the speed of the rear HV minus the preset slowdown speed VDE. If the front HV slows down, it should be the speed of the front HV minus the preset slowdown speed. We then propose a longitudinal and lateral decoupled controller, CC lane change controller. Speed and gap error with respect to the rear agent CV are selected into the state vector. Heading error and lateral position error are selected into the lateral state vector. Acceleration of all CV is selected as the longitudinal control vector. Front wheel angle is selected as the lateral control vector. Moreover, a linearized vehicle dynamics model is adopted. Cost functions are given in quadratic forms. Longitudinal objective is to minimize speed error and gap error with respect to the rear CV. Lateral objective is to change lane at the desired position. Moreover, we have proven this CC controller is with string stability. Oscillation won't increase from the last CV to the first CV along the communication topology. At last, CC backward lane change controller is evaluated on simulation platform joint with PreScan and Simulink. PreScan is an ADAS and IV system simulation software. It follows cinematic physics-based simulation approach. Efficient parametric mass models reproduce system-level dynamics behavior. This simulation is with two objectives. The first objective is function validation. It should verify the function of making space change lane. The second objective is string stability evaluation. The following gap error is adopted as measurement of effectiveness. The environment scenario is illustrated in this figure. It is a typical scenario that a city patrol may encounter. In this scenario, the dark blue vehicles are CVs, white vehicles are surrounding HVs. The orange box is the selected lane change gap. It is between the front HV and the rear HV. A CC platoon is impeded by the surrounding traffic and has to change lane and drive into the ramp. The CC platoon has to, it is considered about two road types are considered, including arterial and freeway. Simulation results are shown in the following. These two figures illustrated trajectories on arterial and freeway. X-axis is the longitudinal position, Y-axis is the lateral position, Z-axis is the time. The dark red line is the trajectory of the rear HV of the gap, and the light red line is the trajectory of the front HV of the gap. Blue lines are the trajectories of CVs in the platoon. The darker the line is, the more rare the CV is in the platoon. So let's focus on the left figure. The darkness blue line first change lane from lateral position 3 to lateral position 0. This means the last CV change lane first, and the lane change of the last CV. After lane change of the last CV, the gap on axis increase between the dark red line and the light red line. It means the gap is opened. And as time goes on along the axis, the blue line change from lateral position 3 to lateral position 0, one by one. It indicates that followers in front of the last CV change lane by turns. The right figure shows the same platoon lane change process.
the result confirms the function of making space for changing. In order to evaluate spring stability, speed perturbation is applied on the last CEV. The speed perturbation is illustrated on the left figure. X-axis is time, Y-axis is the desired speed. The last CEV is controlled to accelerate and decelerate full time on both arterial and freeway. The speed oscillation is 7.2 kilometers per hour. Evaluation results are shown on the right. The upper two figures are gap error trajectories on arterial and the freeway. The darker the line is, the more rare the gap is in the platoon. We can see that the dark lines have larger offsets than the light lines. It means that the front CVs have smaller gap error oscillation than the rear CVs. We know that this communication topology is from rear to lead, so the gap error oscillation reduces along the topology. This confirms the spring stability. The lower figure quantifies the absolute oscillation. From the gap between the fifth and the fourth CEV to the gap between the second CEV and the first CEV, the mean or absolute gap error reduced. This also proves the spring stability. This is my presentation. Thank you.
Thank you, Haran.
Yeah.
I think we have one question from our audience, and I have one question for myself, and two questions from the audience right now. The first question is, how do you decide which gap the rear CAV should cut into? Like,
okay.
How do you decide the gap? Yeah.
Okay. We have proposed a very simple rule-based decision maker. In our decision maker, the gap is selected if it is enough for single CV to change lane. It is selected from the near to far, and this gap is just the lane change gap when a single CV should change lane. And in future research, more detailed platoon decision maker can be proposed for this lane change method. Okay.
Okay, thanks. And the second question is, how many vehicles realistically can platoon and make simultaneously lane change like this? Have you looked at platoon length versus mobility results? Like, how do you decide the length of a platoon?
Yeah. The simultaneous platoon lane change is a conventional platoon lane change method. This method, we have evaluated in the VC platform about when the VOC rate is about equal to 0.75. The lane change capability is reduced a lot. But our proposed method is backward CC lane change method. We have for time being, we have not evaluated in traffic. It will be the future direction in our research. Thank you.
Thank you. And the last question comes from myself, and I noticed you have two different cost functions on one of your slides.
Yeah.
I think JX and JY. Are these two separate questions that you just get the optimal results from each of them, or do you combine them as a kind of optimization problem?
These two optimization problems are separated because in this scenario, CC backward lane change, we don't need the objective to be coupled, because the objective is long-term objective is following, and the latter objective is the change lane. They are not coupled, so the optimization problem should not be coupled. It is not the same with the overtaking scenario, such as the objective will be the optimal and feasible longitudinal and lateral coupled trajectory. So our control don't have to be longitudinal and lateral coupled. Moreover, the decoupled model will bring benefits because the decoupled dynamics will avoid the parameter varying MPC. It will be easy to be solved.
Okay. Understood. Yeah, thank you. That's all for you, and thank you a lot for your presentation and your paper.
Thank you.
Yeah, thank you. Okay, so let's jump to the second session of today's schedule. As you can tell from these slides, we have 3 lightning talks lining up. The first one comes from Bedad Chalaki, the second comes from Shishun Liao, and the third one comes from Yougang Bian. So I will start to share my screen one more time because the first one is a recorded video, but the second and the third one will be live session. Let me stop sharing or I already share sound, so I think that's fine. So the first one again comes from Bedad Chalaki. He is a research assistant at the Information and Decision Science Laboratory at the University of Delaware. His research interests are in network recommendation, optimal control, and machine learning, with an emphasis on transportation networks. In particular, he is motivated by problems related to improving traffic efficiency and safety in smart cities using optimization technologies. Let's take a look at the presentation.
Today, I'm going to briefly talk about a recent paper called Optimal Control of Connected and Automated Vehicles at Multiple Adjacent Intersections. This is the work with my advisor, Andreas Molikopoulos, and I hope you enjoy this talk. So first, let's look at the factors that have motivated us about this research. Adjacent intersections are common in urban areas, which basically one of the problems and challenges in those scenarios is that considering each intersection in isolation have some problems, such as there may not be enough space for each vehicle to adjust its speed. And by considering each intersection in isolation, we may neglect the effects of downstream intersection on the upstream intersection. Also, another approach which is very popular in single intersection is using first in, first out queuing policy, or FIFO, to find the arrival time at basically at the intersection to avoid a lateral collision. But this approach would be degraded if we have asymmetric geometry or if we have asymmetric traffic flow. So if from one leg of intersection, we have high traffic flow compared to other legs of intersection, FIFO would perform worse than the scenario when we have like symmetric traffic volume. So to look at our problems that we're trying to address, we are basically looking forward to find a decentralized coordination framework for CAVs at full multi-lane signal free intersections to improve traffic throughput and improve energy efficiency. We are also allowing vehicles to choose the best lane to improve the throughput of the system. And we further extend our framework to include the steady state error that may occur in tracking the optimal trajectory in the basically vehicle level controller. So we are considering these two intersections, which are close to distance from each other. And basically we have an area which vehicles can communicate with each other. And this area is called control zone. And there's also a red area, which is at the entry of this control zone, and vehicle may change their lane, basically based on the throughput of the system. So if by changing lane, they can improve the throughput of the system, they do so. And we also have two regions which vehicle may have lateral collision. And these two regions are called merging zones. So this is basically one example for two intersections. We generalize this for multiple intersections in the paper. And now basically to look at our framework more carefully, we have our coordinator, which is just like a database. It doesn't make any decisions for the vehicle. It stores information about the vehicle. It stores information about intersections, and those information pass to the CAV when CAV enters the control zone. And in the upper level planning, vehicle chooses arrival time at the merging zones basically on its path, and it will do so by recursively finding the optimal arrival time at each merging zone. And also, this arrival time is found in a way that is energy optimal. So if there is no other vehicles, vehicle basically just cruises with constant speed. It doesn't go with max speed or max acceleration. So if there is no other vehicles in this basically scenario, vehicle just cruises with this its constant speed. And we also have in our upper level planning a lane changing decision, which vehicle may basically choose other lanes. And these two decisions pass to the low level planning, which we have a control effort minimization, which we are minimizing acceleration or deceleration of the vehicle over time that it is inside the control zone, with basically having interior point constraint, which those interior point constraints are the arrival time at different merging zones. And we also have our state and our control constraints, such as rear end safety constraint, control input constraint, and speed constraint. And if the vehicle does a lane changing maneuver, basically if the vehicle's optimal lane is different from the lane that it enters the control zone, it needs to perform the lane changing maneuver as well. So here's a short video of our optimal scenario compared to the baseline scenario when we have traffic lights. And as we can see, in the optimal case, we completely removed stop and go driving, which this would help in improving fuel efficiency that we showed in the paper, and also it improves travel time that we also showed in the paper. But in the right-hand side, vehicle needs to reach a full stop before each intersection. Please send me an email if you want to discuss more about this paper, and you can check my website and our lab's website as well. Thank you all for your attention.
Yeah, as Beta just
Hi,
explained,
everyone.
it's a very interesting talk of multiple intersection, and I suggest everyone to check out his website, and there are a lot of materials over there, a lot of interesting videos about simulation. So our next speaker will be Xishun Liao. Xishun, are you online?
Yeah.
You can start to share your screen. And
Okay.
Mr. Liao is currently a PhD student in electrical and computer engineering at University of California, Riverside. He received a master's degree in mechanical engineering at University of Maryland, College Park, and a bachelor's degree in mechanical engineering and automation at Beijing University of Post and Telecommunications. His research focuses on decision-making, driver behavior, and connected and automated vehicle technology. Go ahead, Hasan.
Yeah, hi. Thanks for attending this workshop. And the topic of my presentation is a game theory-based RAM merging strategy for connected and automated vehicles in the mixed traffic. Yes, we may have experienced some unsafe and inefficient merging in our life, as this video shows. And besides short RAM, length and limited vision, bad competition and complex interaction make the RAM merging very even difficult. And so, as this figure shows, we have sometimes we have a mainline vehicle A and a RAM vehicle B in conflict. So we need to decide who go first. In mixed traffic, any well-planned merging sequence may be interrupted by the next vehicle. And the merging sequence needs to be decided dynamically, even we can say at each time step. Therefore, we want to bring in the game theory. So for this case, we can formulate a game where A and B competing for the merging priority, and each vehicle tries to maximize all reward and by choosing either to be a leader or a follower, and each vehicle try to we can figure out what's the natural equilibrium and then find out the answer. So this workflow designed for CAV, which can determine a dynamic merging sequence and provide corresponding longitudinal control. And each CAV will walk through the 6 main module at each time step from module A to module F. For module A can project detected vehicle into future to see if there any conflict exists in a given prediction window. If there's a conflict, and avoiding it should be always be our first choice. So we have our module B decided for the mainline vehicle. The vehicle in mainline 1 can always change its lane to the left in advance to avoid the conflict with the RAM vehicles. So what if the conflict cannot be avoided? Then we would need our following game theory decision-making modules. First, we need module C to categorize what kind of the types of the potential competitors. Is it a CAV or Lex vehicle? If there are 2 CAV in the game, module D will form a cooperative game, and these 2 CAVs can communicate with each other and make decisions together. Otherwise, the CAV will maximize all rewards. And then we have module E for disseminating the merging sequence. By considering the cost function that have the merging risk, mobility, and comfort, it can select action either being a follower or leader for our ego CAV. Then the final module is the acceleration control module to execute the decision from the module E, including longitudinal speed control, lane checking, and lane changing behavior. So here comes the part that how we evaluate our, I saw some, and here comes the part of how we evaluate our algorithm. And in like many current simulation platforms, such as we have Unity driving simulator and Sumo as their traffic simulator, have their pros and cons. And only using one of them is not enough for studying the mixed traffic and human interaction. So to carry out this a mixed traffic flow simulation, we uniquely built a co-simulation platform that consists of a driving simulator and a traffic simulator, which can provide an authentic traffic environment. In this platform, we model a one-to-one real-world scenario in Unity, and as figure B shows, we program CAV in red and Lex vehicle in white, and the spreads of the red line indicate the detection range of the radar of the CAV. And figure C shows how that the Sumo and Unity platform synchronize with each other with a two-way UDP communication. And this is the result video we carry out we evaluate our algorithm in our platform. First, the first video presents how CAV in this yellow circle perform the car following behavior under the control of our acceleration module. And we have our second video shows how does the conflict avoidance of the mainline vehicle works. In this red circle, these two CAV can avoid the conflict. And the third video shows how the CAV react to the Lex vehicle, and then following some the coordinated sequence and finish the RAM merging. And finally, we verify our algorithm in a traffic flow level simulation with considering different penetration rates from 0% to 100% from light traffic to congested traffic, the average speed of the traffic flow can be increased up to 210%, and the fuel consumption can be reduced up to 54%. And finally, the driving volatility can be stabilized to a 0% level. So that's a very good result for using this game theory-based merging algorithm. Yeah, so much for that. Thanks, everyone.
Thank you, Hysan, for this quick talk. If anyone has any question, please feel free to add in the chat box. Maybe Hysan will ask maybe one very quick and easy question. What is the next step of this research based on whatever you have done for the game theory-based decision making? What is the next step?
Yeah, the very the most emergent one is the prediction, right? We need to project our vehicle in the future to see if there is conflict, and once more, and we also need to know other legacy vehicles' behavior then we can make our decision. So our next step would be the behavior prediction.
Mm-hmm. Great. And two questions come to us. One is, for highway merge, how is the right of way represented in the utility function design?
Oh, okay. So yes, the right of way is included in the risk term in the cost function. We can, that's much of a program and mathematical problem. We can add up the we can increase the risk on the RAM vehicle and let them think the merging from the RAM to the main line would have a higher cost than the risk in the mainline vehicle.
Okay, thanks. And the another question is, do manual vehicles still play in the game? Like the human-driven vehicles, are they still there?
Oh, in this current stage, we didn't include human-driven vehicle, but yeah, of course, in next stage, we can include some human-driven vehicle, which are driving with some external device like Logitech driving wheel into our Unity platform.
Mm-hmm. And maybe the last question is, have you looked at penetration rates that are small, like 5 to 10% of the vehicles, like connecting automated vehicles?
Yeah, I think that would be a very good question. And we didn't show, since the interval are too small, we didn't show it on our presentation and our paper. But I did carry out some simulation on 5% or 10% penetration rate. But the result is very close to the to 0% penetration rate. And since one we can think about that, one CAV can only affect one-time merging, and the overall increasing need a lot of CAV, of course.
Mm-hmm. And maybe a quick follow-up by Surrogate as well. When do you start seeing a significant difference when you increase the penetration rate? Is there any jump at any spot?
Okay. Actually, according to the result, in 30% penetration rate can make a big difference. And yeah.
30%. Okay, that's a sweet spot. Okay. Yeah. Thank you, Hysan, one more time. And anyone have any follow-up question to Hysan, please feel free to add in the chat box. Our next presenter, Yogang, please feel free to share your screen. And Dr. Yogang Bian is currently an assistant professor in Hunan University in China. He received the bachelor and PhD degrees from Tsinghua University in 2014 and 2019, respectively. From 2017 to 2018, he was a visiting student with the Department of Electrical and Computer Engineering at University of California at Riverside. His research focuses on cooperative control and distributed control with their applications to connected and automated vehicles. Yogang, the stage is yours.
Okay, thanks to Dr. Wang's invitation, and it's my honor to give a presentation on the workshop. The title of my talk is Stabilizing Mixed Traffic Flow via Control of Connected and Automated Vehicles. And I'm Yu Gangbian from Hunan University. Okay, the first, as we all know, human driver is the main cause of traffic jams. This is a research by the Ford by comparing the cases without ACC and with ACC. With the emerging of the CEV technique, more and more researchers are focused on the mixed traffic flow. So for this figure, the blue cars are the connected and automated vehicles, and the gray ones are the human-driven vehicles. So in this mixed traffic flow, there are too many discussed questions. The first one, how does a small scale of cabs benefit the traffic performance? There are already some studies on this topic. The second question is, how will the formation and penetration of cabs influence the mixed traffic flow? There are already some work on the merging control in mixed traffic flow, but there is still there are no studies on platoon control. So our study is going to answer this question for the platooning control in mixed traffic flow. So we consider such, this condition. There is one connected and automated vehicle, and it has M preceding human-driven vehicles and N following human-driven vehicles. So the CAF can obtain these human-driven vehicles the information. So this group of vehicle consists of a mini platoon in the traffic flow. So why do we consider the human-driven vehicles behind? As we know, it's traditional to consider the human-driven vehicles ahead in the framework of connected and cruise control. But in our study, we consider not only the looking ahead case, but also the looking behind case, because we believe this can help in increase the string stability of the mini platoon, which we are given below. And the second question is, how do we design the controller considering the HDVs both ahead and behind? So for an HDV ahead, we can use the OVM model, OVM to model the spacing policy. But for the looking behind the case, we use an inverse OVM, and then we can use a linear controller to address the control problem. Here, the position and velocity control gains are alpha and beta. So under these settings, we analyze the string stability of the mini platoon. We use the head to tail transfer function to model this problem. And the transfer function is given here, where yn tilde is the velocity tracking area of the vehicle n, and y0 tilde is the velocity vibration amplitude of vehicle 0. So from this transfer function, we find that the position of the cab or the index I does not affect the transfer function. On the contrary, the topology M and N, the platoon size N, and the control gains alpha and beta, all will affect the transfer function. Then we are going to analyze the effect of the formation and the penetration of the cabs in the mini platoon. Okay, the first result is that given a fixed N, we analyze the transfer function for 3 cases. Case A is M is 1 and N is 5. So the cab have 1 preceding vehicle and 5 following vehicles. And case B is M equals 3 and N equals 3. And case C is M equals 5 and N equals 1. From these figures, we know that more information from the following human-driven vehicles use better string stability. This is opposite to our traditional concept on string stability, because we usually use many preceding vehicles, but this result tells us more information from the following human-driven vehicles also help guarantee string stability. And the second result is on the penetration of calves. We consider a fixed N and a fixed M. So in this case, the figures show the stable domain of the control gains, alpha and beta. So as the figure shows, with a given upper bound of alpha and beta, the maximum number of vehicles in the platoon is N to guarantee head to tail string stability. This tells us that when connected and automated vehicle can stabilize a maximum of 7 human-driven vehicles. So if all the vehicles in the highway is organized in this way, then the penetration, the minimum penetration is 1/7 to guarantee string stability. Okay, that's our results on the mixed traffic platooning control. Thank you.
Thank you a lot, Dr. Ben. Right on time. Ben, if you go back to the previous slide, I have actually maybe 2 questions, and I think it's very interesting. The first question is about the simulation. When you said maybe more information from the following vehicle will have better string stability. But for the following vehicles, are they modeled as the same vehicle type as the preceding vehicles, or those different vehicles, because those are all human-driven vehicles, they have different kind of models of the parameters?
Actually, the following and the preceding human-driven vehicles are based on the same model.
Mm-hmm.
So they are both based on the optimal velocity model.
Okay. Why do you think the cost of that? Why is more information from the following vehicle might have better string stability?
Okay. As shown in the figures, if there is only one preceding vehicle, the amplitude will be the shocking wave will be amplified by only once, and the connected and automated vehicle will deteriorate the amplitude, and the following human-driven vehicles, though they will still amplify the shocking wave, but the amplitude is still limited. On the contrary, if there are 5 preceding human-driven vehicles, the amplitude will be amplified by 5 times, and then it deteriorates by the connected and automated vehicles. So in this case, the absolute amplitude will be larger than this case. So this tells us following vehicles information is better.
So maybe the conclusion from my understanding is that the further your vehicle CAV is downstream, the better the string stability will become, because that vehicle will affect more vehicles upstream.
Yeah, that's the case.
Yeah, that's a very good conclusion. And maybe my second question is the same as what Surrogate brings up in the chat box. What gain ranges in terms of the alpha and beta? Maybe if you go back to maybe slide 4, I don't know. Would you expect to tune your CAV? How do you tune those alpha and beta of your algorithm?
In our algorithm, we didn't tune, but we try all the combinations of alpha and beta. So we give an upper bound of alpha and beta as 3. So in this case, the blue regions represents the stable domain for string stability. So in this case, we can know how large the region is to select alpha and beta. So a small range means the string stability can hard to be guaranteed, and a large region means that the string stability can be easily guaranteed by selecting alpha and beta.
And he asked, would some of those values be unreasonable for vehicle dynamics constraints? Do you consider any of the real vehicle dynamics?
Actually, for with the connected and automated vehicle, we use a 3-order linear model. But for the human-driven vehicles, we use OVM. So the real dynamics, including the non-linearities and maybe the air drags, the tire dynamics are not considered in our study.
Understood. Yeah, I think that's it. Thank you a lot for this very interesting presentation.
Okay, thank you.
Yeah. Okay, let me share our schedule one more time. Our next session, our third session today, will be another 3 full talks. First come from Yong Wang, and then Yimin Zhang, and lastly Sergey Abatisov. Yong, are you there? Can you start to share your screen? Okay, great. So next speaker is going to be Mr. Yong Wang. Mr. Wang is currently studying at the College of Computer Science in Chongqing University. In 2019, he received a bachelor degree in computer science and technology from the College of Computer Science, also in Chongqing University. His current research interests are vehicle network and intelligent network vehicle test. Yong, please go ahead.
Hello everyone, I'm Yong Wang from the Department of Computer Science, Chongqing University. The topic of my paper is research on optimization and evolution method of car following model based on sumo application test scenario. My report includes 5 aspects. 1, introduction. 2, preliminaries. 3, a level model. 4, experiment analysis. 5, conclusion. In the first part, introduction, the congenital twins is considered as a new test approach for CAV. The effectiveness of DT based on in-chamber test largely depends on the rationality of DT scenarios, which should meet the requirement of continuity in space and time. Hence, the realistic of vehicle mobility model should be considered. In terms of vehicle mobility model, Cross-S establish a model based on the safe speed. Later, some scholars optimize this model. However, the improved model based on Cross doesn't consider the following model of the acceleration process and the influence of the dynamic time headway on the following state. In this paper, based on the Cross model, the influence of the speed of the following model on the following state and the problem of acceleration change abruptly in the following model are considered. Analyze the braking process of the vehicle and consider the dynamic time headway, and optimize the Cross model to make the simulation scenario more reasonable. The second part is preliminaries. A test system is designed to support in-chamber V2X test. The proposed system includes 3 key components, which are scenario generator, nexus, and communication node matrix, and the EMC tester. All test cases should following correspond specification and are generated by a scenario generator. The communication node matrix, which includes 14 OBUs and 3 RSUs, generates a corresponding message according to the output of the scenario generator. EMC tester is used to evaluate the operating performance of the vehicle equipped with the DUT under the circumstance of high power radio radiation. The corresponding test procedure includes the test case selection, the traffic scenario injection, and the test data code and analyze. As mentioned earlier, in the proposed system, all traffic scenarios are generated by Sumo. The generation proposed includes the three key points. The road network generate, the vehicle information generation, and the chassis background black control scenario. The third part is the improved model. In the original crust model, the safe falling model is defined as Formula 1. Consider the influence of falling vehicle velocity. We defined safe falling distance as Formula 2. Based on the Formula 2, I construct the deceleration model, acceleration model, and acceleration deceleration conversion model. First, let's expand the deceleration model. Obviously, deceleration progress is related to the braking progress, which is denoted in Figure 1. It includes the driver's reaction phase and the braking force growth phase and the continuous braking phase. Unless the stage, we can get the distance of each stage as Formula 3, 4, and 5. Summarizing the above stage, the three stages, the displacement of the following vehicle in the full braking stage is defined as Formula 6. Consider that the vehicle in front can brake at any time. The reaction stage of the driver of the leading vehicle may not be counted. So the displacement of the leading vehicle in the full braking stage is defined as Formula 7. Combine the Formula 2 and 6 and 7. The safe velocity is defined as Formula 8. Finally, the vehicle desired velocity is defined as Formula 9. Secondly, let me explain the acceleration model. Here we import integral theorem to calculate the acceleration distance to get smoothly acceleration progress. Combine the Formula 11, the acceleration time, and the Formula 12, the vehicle driving boundary conditions. The maximum safe velocity in acceleration curve form model is defined as centimeter 13. Third, let me explain the convention machine. The acceleration deceleration progress is shown in the Figure 2. From the 10t to 10t at t, the position of the falling vehicle and the position of leading vehicle could be denoted as Formula 14. The distance between the two vehicles and the initial distance between two vehicles is defined as Formula 15 and 16. Note here, if Vf is greater than Vl, an acceleration state should be changed to deceleration, and the converse is also true. And the fourth part is conclusion. Here we take a vehicle following scenes as an example to construct the sumo simulation scenario. Corresponding road and the vehicle compartment are set in table. The microscope selects the velocity of the falling vehicle and the probability of the vehicle stepping change as the evolution index. Here, the original cross model and the improved model are used as a contrast to verify the effectiveness of proposed model. The vehicle change on the falling vehicle is shown in this figure. As shown in the figure, the velocity curve of the proposed model is relatively smoother than the original cross model, which solves the problem of the velocity stepping change. As shown in the table, comparing with the original cross model, the proposed model presents no stepping probability, then solve the velocity stepping change problem. To display the performance of sumo-based simulation, here we select a cross-road scenario: 3 gorges, branches road, and shopping bar station North Road, Chongqing. As an example, 16 hours traffic data of the October 21, 2020 year are used to generate simulation scenarios. As shown in the table, compared with the original mode, the travel time, average vehicle density, road occupants, road average waiting time of the improved model has been significantly reduced, and the vehicle velocity has been significantly increased. A test system is designed to support the in-chamber V2X test, where the text example is given like this. And the fifth part is the conclusion to match the requirement of V2X oriented test. In this paper, we designed test procedure and explain the corresponding scenario control progress. Moreover, to improve the reliability of the simulation, we define safety following distance, which consider not only the distance between the leading and the following vehicle, but also the following vehicle's velocity. Then an improved cross model, which includes the deceleration model, acceleration model, and acceleration deceleration conversion model, is proposed. Simulation results show that the proposed model could reduce the probability of the velocity stepping change and perform a smooth vehicle falling effect. And test system is designed to support in-chamber V2X test, where a test example is given. In our future work, we should consider communication interface and optimize sumo lane change model to match the demand of the V2X application test. That's all my presentation. Thank you for listening. If you have any questions, or to contact us with the email in this page. Thank you.
Thank you, Yong, a lot for this presentation. I do have a very quick question for your simulation. I remember that you mentioned you use data from the real world and you run a simulation for 24 hours. In that data, do you also consider different vehicle types in your simulation, or you consider all vehicles the same type, the default vehicle type? Are you speaking? If you're speaking, you're muted. Hello, Yong? Disconnected. Anyway, we can go ahead to our next presenter, and we can always reach back to Yong later through email or through this chat box. Let me restart my share screen. And we have two more full talks today. One is from Yimin Zhang from Tongji University, another one from Surrogate from Toyota. Yimin is going to talk about an cooperative adaptive push control against varying vehicle loads. Yimin, are you there? Can you start to share your screen?
Hello, can you hear me?
Yeah, Yimin, yeah, I can hear you right now. Yeah, you can start to share your screen.
Hello?
Yeah, can you hear me?
Hello, can you hear me?
Yes. Yes, Yimin, you can start to share your screen.
Yeah.
Our next speaker will be Mr. Yimin Zhang. Mr. Zhang received the bachelor degree from Shenzhen University in Shenzhen, China in 2016, and master degree in traffic engineering from Tongji University, Shanghai in 2019. He's currently pursuing the PhD degree in traffic engineering at Tongji University, Shanghai. His research interests include connected vehicles, intelligent transportation systems, and cooperative driving. Yumi, you can go ahead and start your screen, start to share your screen and start your presentation.
Yeah. Wait a moment. There is some problem with my connections. Wait a moment.
Yeah, sure. Take your time. And maybe while Yimin is setting up his computer, I will do a very quick overview of tomorrow's program again. Tomorrow we have speakers from University of Michigan, from Stanford University, from Vanderbilt University, and we will have also speakers from industry, from Leaf and Toyota. So please come back to join us tomorrow at the same time. And if you have any question, please feel free to let me know through email. Yeah, Yimin, we can see your screen, and please go ahead.
Yeah, thank you for introduction. Hello, everyone. My name is Zhang Yimin from Tongji University, China. The topic of my presentation today is an adaptive CSCC against varying vehicle loads. And my presentation can be divided into 4 parts. Now let's begin with the first part, motivation. As we all know, we are now suffered from severe traffic problems, including traffic jam, traffic accidents, and traffic pollution. To cope with these problems, the industry has proposed the idea of connected and automated vehicles. Now, let me clarify these 2 different concepts. For the autonomous vehicle, it focuses on imitate human drivers. In other words, it can play the role that human drivers played in the past, including lane keeping, adaptive cruising, or collision avoidance. For cooperative automation, it focuses on cooperation. It can smooth the traffic oscillations caused by the human drivers and improve the traffic efficiency. Generally, there are 4 major benefits that CSCC can bring. First, it can improve traffic safety by eliminating the human driver's reaction process. And secondly, can smooth the traffic oscillations caused by human drivers. And third, it can save labor force because only the leading vehicle needs a driver, which is very beneficial for companies' cost control. And to be last, it can reduce fuel consumption. According to a theoretical analysis, the fuel consumption of each vehicle in a platoon can be reduced up to 10%. To be further, from the figure presented on the right, we can see that the traffic capacity per lane can be doubled if the penetration rate achieves 100%. Okay, now let's continue with the second part. First, that is the highlights of features. First, our controller is modeled in a mixed function domain. It follows a constant time strategy. To be further, it can eliminate the prediction process by checking the leader vehicle's history information. Or in other words, we didn't improve the prediction accuracy. We just eliminate the prediction process. In this way, it can greatly enhance the string stability and improve control accuracy. Secondly, we introduce a dynamic metric control or DMC controller to provide a bridge linking upper level command and low level controller together. Meanwhile, it can adjust controller parameters adaptively according to real-time feedback. Generally speaking, it can improve driving safety and eliminate the brake jerk. Okay, now continue with the third part. Our general architecture follows a classic form, including the perception, planning, and the level control. To be specific, the planning process includes the gap regulation controller and the DMC controller. The gap regulation controller will export the expected acceleration series, and the DMC controller will generate a revised acceleration series to the low-level controller. And this slide shows the difference between time domain and space domain. As is shown in the figure, the solid green curve is the shows the distance, time distance relationship of the living vehicle. If you want to keep a constant distance gap, you can just shift the curve along the y axle. And it means you have to keep the same driving behavior at the same time. And in time domain, the derivative is with time. For example, the velocity equals to the distance divide time. While in space domain, it means you can shift the curve along the x-axis. It means you have to maintain the same driving behavior at the same position. And in space domain, the derivative is with time. For example, the corresponding variable of velocity in space domain is called slowness, or we simplify it as W. It equals to time divide space. It is the the reciprocal of speed. And this slide shows the original form of the gap regulation controller. It is modeled in space domain where all variables are with space. The state vector includes two items, including the difference between the desired time headway and the actual time headway. And the second item is the difference of the slowness between leading vehicle and the equal vehicle. And the control vector is called moderation. It is the derivative of slowness. The original form is modeled since the original form is modeled in space domain, and the control vector is a little difficult to understand. And it is difficult to give a constant constraint and weight to cope with all driving conditions, because the controller B has a cubic relationship with acceleration. So we make some transformations to have the controller modeled in a mixed function domain. The controller has been transformed from moderation to acceleration. And this transformation aims to make it more applicable to various driving conditions and more intuitive to be comprehended. And in this way, the system dynamics has been transformed from a linear time varying problem to linear time invariant problem to linear time varying problem. And the C matrix is the major disturbance. The cost function follows a classic quadratic form with three weight factors. You can set different values for each according to your preference. And the solution is based on dynamic programming. The computation time is small enough to be applied in reality. Since the system response in real world can be highly nonlinear and time varying, the assumption that the command can be executed immediately or it follows a first order process is not realistic enough. And it is the common methods in the past literature. Based on this, we proposed a dynamic metric controller to link the upper-level controller and the low-level controller together. The system dynamics of the dynamic metric controller is modeled based on the response curve of the vehicle. And the purpose of this controller is to make the actual acceleration as output as close to the expected acceleration as possible. For example, if you want to realize an acceleration of 1, probably you have to give them a command of 2. To be further, the parameters would be collaborated according to the feedback. In general, the DMC controller is able to be solved and calibrated in real time. Now let's go on with the fourth part, evaluation. This slide shows the simulation architecture and experimental settings. The joint simulation architecture platform is conducted based on CASIM, PERSCAN, and Simulink. The traffic scenario is long straight road, and the test vehicle is chosen to be the Mazda Z8. Here are the settings for the experiment. And we have standardized the driving cycle for each run. The driving cycle of the leading vehicle includes 4 stages: acceleration, fluctuation, cruising, or deceleration. In the experiment, the leading vehicle is assumed to be an ideal vehicle, which is more critical to the experiment. And for the acceleration, in the stage, the vehicle will accelerate at specific acceleration until it reaches the desired speed. And for the fluctuation, the leading vehicle would accelerate and decelerate repeatedly during the process. And for the cruising, the leading vehicle will keep a cruising stage at the desired speed. And for the deceleration, the leading vehicle would decelerate at a fixed rate until it fully stopped. This slide shows the performance under different speed conditions. And the first row shows the velocity of the platoon. The blue curve is for the first vehicle, and the red curve is for the second vehicle. The green curve is for the third vehicle. The second row shows the acceleration of the platoon, and the third row shows the time gap error for the controller. The result shows that the controller had a good performance under different speed conditions. And this slide shows the performance under different loads. It shows that even when the loads are varying, the controller still had a good performance. To be further, we utilized the algorithm in trunk platooning. And the result, the test vehicle is a SAIC Hongyan trunk, and the load for second vehicle is 20 tons, and for third vehicle is 10 tons. Actually, it is quite homogeneous. And the result shows that the controller can perform well even under heterogeneous trunk platooning driving conditions. You can just look at the figure above. The blue curve is the leading vehicle's speed profile, and the red one is the speed profile for the second vehicle, and the yellow one is for the third vehicle. You can see from the figure that the disturbances caused by the leading vehicle can be smoothed by the platoon, because the fluctuation of the third vehicle is the smallest. And we also make a comparison between a controller of a literature. And the result shows that our controller outperforms the benchmark controller. And in that controller, you can see in that homogeneous trunk platooning situation, the third vehicle, it fluctuates much greater than the first vehicle and the second vehicle. Okay, now let's go on with the last part. The results shows that our proposed algorithm has the potential to cope with the heterogeneous trunk platooning. And it has been verified under different driving conditions, including the different driving speed, different oscillations, accelerations, and different loads. And to be further, we believe the constant time gap strategy is most suitable when concerning the string stability, because when considering the uncertainty and stochasticity of human driver leaders, speed varies rapidly. So the safety of the CSC platoon cannot be guaranteed when keeping a constant space gap, since the predicting future is quite difficult. Okay, so that's the end of my presentation. Thank you, all of us, and please feel free if you have any questions.
Thank you, Yimin, for this presentation. I have 2 questions, if you don't mind. The first question is regarding the computational time. I think you mentioned 4 milliseconds for your algorithm. Maybe my question is, that 4 milliseconds, is it based on the optimization of your algorithm for just one vehicle, or for multiple vehicles, or one vehicle on each of the computer? I mean, how do you calculate that time value?
Yeah, actually, we both tested the time in our laptop and the computer on vehicle. Actually, both the time is less than 5 seconds. Yeah, so I think it is quite applicable into real application.
And the results of the algorithm is just for one time step at a time, or it will be for multiple time steps?
We would update 100 seconds each time. Actually, we have done some few tests, but not presented in this slide. And we will update the controller each 100 seconds, and it is for the whole calculation. Okay,
understood. Yeah. Thank you. And the second question, if you go to the trajectories of different vehicles, the results that you mentioned there, the second vehicle has a load of something, the third vehicle, the truck platooning. And I noticed, for here, thank you. The speed time curve, the plot on the right, the top one, is the first vehicle simulated vehicle, or is also a real vehicle that you do the testing?
It's a simulating vehicle. Actually it is an ideal vehicle, because we think in this way it will show some much difficult experiment condition. Actually, you can see the driving curve of it. It will accelerate and decelerate abruptly. It means the jerk is infinite. So I think it is good for the simulation, because it's the hardest setting.
Yeah, that's my concern, because I think it's not realistic. But for your second vehicle, how do that vehicle follow the first vehicle? Is it just a simulated parameter input to the controller of your second vehicle?
Yes, it will get the information from the leading vehicle and calculate its command, and then the third.
Okay, understood. All right, yeah. If anyone have more questions for Yimin, please feel free to add in the chat box. But thank you, Yimin, for your presentation.
Thank you.
Our last speaker today will be our next, of course, Dr. Sergey Avadisov. Sergey, are you there?
Yes, I'm there, and
great.
you can hear me, right?
Yeah, I can hear you. You can go ahead
All
and
right,
share your
so
screen.
I'm going to share my screen.
Dr. Sergey Avetsov is currently a research scientist at Infotel Labs, Toyota Motor North America, here in Mountain View, California. He received his master's degree and PhD degree both in mechanical engineering from the University of Michigan and Ann Arbor, United States, in 2016 and 2019, respectively. His current research interests are cooperative perception and cooperative maneuvering of connected vehicles, 5G communication technology, and applications of vehicle connectivity to ADAS. Sergey, the stage is yours.
Thanks for the introduction, Ziran. So today I'm going to present the work where we assess the awareness of connected vehicles in mixed traffic environments through something that we call perceived safety. And this work is related to a paper that just got published with my collaborators at Infotech Labs with Dr. Ahmed Sakir, who was in Infotech Labs until recently, Takamasa Higuchi, Akihiko Yamamuro, and Onur Altintas. And the reason why we look at awareness of connected vehicles and develop this perceived safety framework is because vehicle-to-everything communication is rapidly developing in terms of the different message classes that are being proposed. So right now, both SAE, the US Standardization Organization, and ETSI, the European Standardization Organization, had these basic safety messages or cooperative awareness messages for a long time, where a vehicle that's connected can share information about its own state. For instance, the position, its GPS speed, its heading, as well as maybe its size. So information about what it is currently doing, where it is currently located. And now, however, to improve the cooperation between vehicles, multiple different messages are being proposed, in some of which a connected vehicle would not only have the opportunity to share information about itself, but also about objects it detects using sensors. So for instance, in this case, this green car is able to send information about this braking vehicle that's being detected by it to this yellow car. And then this yellow car has an enhanced awareness of its surroundings, especially if that vehicle that's currently braking is not connected. And benefits of these so-called sensor sharing messages or collective perception messages, and the specifics as well as how you call it depends on the standardization organization, are quite clear, especially in mixed traffic now that you can detect unconnected objects and account for them, including vehicles. And multiple research has looked at using CPMs or SSMs to show that they can allow to detect significantly more objects than these basic messages that we had before. However, as a trade-off, typically these messages are a lot more sizable. So they contain a lot more information. They contain both the sensory information as well as all the objects potentially, or subsets of the objects that the vehicle detects. So it's a very cumbersome message, especially with, let's say, current spectrum limitations. So one of the things that we were thinking about is that the importance of detected vehicles and objects is very scenario specific. For instance, if a vehicle is coming up to an intersection and we want to make sure that we yield to all the pedestrians, we want to be aware of the pedestrians that are right there or crossing the intersections. We might not care about pedestrians that are 500 meters away, even if our sensor sharing messages are able to deliver that. So the goal of this framework that we develop is how much do CPMs or SSMs, these new messages, benefit in detecting critical vehicles? And so what we took as a baseline is a multi-lane highway environment. And in general, you can have different traffic environments. We have this yellow Ego vehicle, and it's traveling in a mixed traffic environment where we have connected and unconnected vehicles. And in general, when traveling on a highway, vehicles would want to perform car following and lane changes, and they want to have awareness during those maneuvers. So this means that the area of interest is usually going to be the same lane as the ego vehicle for car following, or the adjacent lanes, which are going to be, we want to pay attention to for lane changes. And then what we do with this perceived safety is we want to figure out which vehicles are critical to us. So for instance, in this highway driving environment, usually you can get in trouble by having a vehicle approach you too fast from behind. This we call the rear end safety condition. In this case, this remote vehicle approaches this ego vehicle quite fast, and that could lead to a conflict or a collision.
It seems like Sergey is disconnected. Let's wait for him a little bit. And just a preview of tomorrow's calendar. We will have two full talks at the first session, and followed by 3 lightning talks. And the last session will be another two full talks. So again, the same time tomorrow. Please join us if you have time. And let me pin Sergey.
I'm back.
Great, Sergey.
Yeah.
You can start to share your screen one more time.
Yeah, sorry for this. The video got disconnected.
No problem.
Yeah. So yeah, we were talking about these safety conditions, and I'm going to share screen. Yep. Let me just move this out of the way. Hello?
Yes, I can hear you.
Yeah,
It looks perfect. Go ahead.
Yeah, great. So we had these 3 ways in which the vehicle can get in trouble, either through the rear end safety condition, when again this car approaches our ego vehicle fast from behind, and we could risk we could risk a conflict or a collision. Similarly, the frontal safety condition, where this ego vehicle might approach another vehicle fast from behind, where again you could have a conflict or some sort of collision. And also you could have a sideswipe condition where these vehicles are traveling side by side, and this ego vehicle might merge into another vehicle when it's changing lanes. So these can be related to something called surrogate safety measures, which are popular metrics for different sort of traffic scenarios that tell you how critical traffic scenario is, and how severely the safety is violated in any given scenario. So for highway driving, such metrics include the time to collision and minimum acceleration. And for instance, if you look at intersections, things like post-encroachment time becomes becomes an important metric. So in this case, we can relate each of these safety conditions to a surrogate safety measure. For instance, here, the rear end condition, we can say that if the time to collision between the ego vehicle and the remote vehicle is less than a certain value, this vehicle is critical to us. We must be aware of it as the ego vehicle. We must be able to detect it so that we can respond to it properly. Then similarly for for the frontal condition, we must be aware of this vehicle in front. And these two conditions in general hold for both the same lane, that's for car following, as well as adjacent lanes. So we want to be able to detect vehicles that are traveling far behind us and approaching us, as well as if we're approaching any vehicles fast in the other lanes through this time to collision criterion. And the sideswipe safety condition is simpler, so it does not consider any surrogate safety metric. Rather, it just looks at if the vehicles aren't completely ahead or aren't completely behind of our ego vehicle. And the way one could implement this is, let's say for a realistic highway driving, the NGSIM I-80 data set, which contains data for the evening rush hour in California. And in this case, it has 15 minutes of real highway trajectories of vehicles along the road. And we can take that data set and we can look at a specific ego vehicle over here that's going to traverse this data set. In this case, it uses vision sensors, which are, in this case, could be a camera or a LiDAR with, or a radar with occlusion. And what happens is this ego vehicle can detect vehicles with its sensors given by the blue dots here. And if we play this animation, what you're going to see is there's a few blue dots, but there's also some red crosses. Like in this case, you have a couple vehicles behind. And these are all vehicles that this ego vehicle must detect because they are critical, because we want to be aware of those vehicles according to our safety conditions, but we aren't able to be aware of them because we're either occluded or our sensory range is lacking in this case. And to summarize this sort of lack of awareness of this vehicle, what we say is the perceived safety error is the amount of time that the ego vehicle is not aware of at least one critical vehicle, one vehicle that we define to be critical through our conditions. And in this case, that's 31% of the time. So we can improve on that. And in this case, let me repeat, this was without connectivity. So the way that we improve on that would be with connectivity. So in this case, we can examine a couple of scenarios. So we can look at the same vehicle in the same sort of traffic situation, but in this case, we have 50% CV penetration and connected vehicle penetration, and our ego vehicle is also connected. So it can receive these basic messages like basic safety message or cooperative awareness message, and use that information to be aware of all these connected vehicles. And naturally, what happens here is you see a blue dot on every connected vehicle in this animation, so we're aware of them. But there's still one unconnected vehicle that we might not be aware of, and it's kind of approaching us a little bit fast. So maybe we would want to make a lane change to move out of the way in this case, for the sake of, if we were aware of it. So we do better at 50% penetration with these messages, but we still don't have full awareness. Full awareness, however, is granted to us by using these cooperative perception messages, where these green cars are also using similar sort of perception sensors as the ego vehicle. And in this case, we have full awareness at 50% penetration. So pretty much we're aware of all the vehicles in the environment, because those other vehicles are also sending their sensory information in addition to us getting our own sensory information. So that's the visual benefit of these cooperative perception messages in mixed traffic. So of course, that's very nice that we can do this at partial penetration. And to look at the kind of overall results, what we see here on the figure on the left is the perceived safety error of all the vehicles that we examine in this data set versus the penetration of connected vehicles for when we use the different messages. So on the at 0, what this means is these are two box plots for when there's no connectivity. So these two box plots are the same for CAM and CPM, because in this case, these messages are simply not used. There's no one to send those messages. And here we selected vehicles with perceived safety error that in the NGSIM data set that ranges from roughly 10% to 65% of the time. There is a vehicle that they should be aware of according to our conditions, but they're not. So we improved that with the basic messages like the cooperative awareness message, where vehicles transmit information just about themselves. And the improvement, we can get close to full awareness when we get close to 100% penetration, naturally, because then all the vehicles are sharing their state with us and we know about them. But with CPM, we can do this a lot quicker. So in fact, at 20 to 30% penetration, we are already fully aware for all the connected vehicles of what's going on. So this is nice in the sense that the cooperative perception is a really strong argument for early adopters of V2X, because here, once you achieve that penetration of 20 to 30%, you're fully aware of what's going on, and you also get significant benefits even at 10%. But there's always a trade-off, and I alluded to this trade-off a little bit earlier. So if you look on the graph on the right, what this plots is, this plots the channel use or the channel busy ratio, which is the wireless channel in which these vehicles are transmitting these messages. And what happens is here, the channel busy ratio increases pretty much linearly with the penetration. And you can see that makes sense because the more connected vehicles, the more messages you send, but also the CPM one is a lot higher than the CAM one because of that extra information transmitted. And furthermore, if the channel busy ratio is above 0.6, typically at that point you start getting into packet collision and packet drop effects, which limit the information being sent. So in those CBRs above say 50 to 60% penetration, you're going to have difficulty sending CPMs, and in that case you'll get less than ideal performance. So what this means is, despite the kind of strong performance for low penetration, you must really manage this cooperative perception when you share information about things you detect, objects you detect, as the penetration increases. And this should be done actively, and perhaps with as the penetration increases, as well as taking into account which vehicles are critical or not. So as a summary, what we did here is we introduced this perceived safety framework to account for the critical vehicles and see how do different message types as sensors account for the vehicles that a cooperative or that a connected automated vehicle is aware of. So we considered a traffic scenario, like in this case, the highway. We could do the intersection. In fact, that's what we're working on now. And then what we do is we select vehicles of interest that we want to examine the awareness of, like this ego vehicle. Then we use surrogate safety measures like time to collision, minimum acceleration, or the different encroachment times, depending on the traffic scenario, as well as right-of-way rules to determine the critical vehicles. And lastly, we check if sensors and or V2X communication give the ego vehicles the appropriate awareness of critical cars for that traffic scenario. And in this case, we considered the highway and investigated how these cooperative perception messages perform with respect compared to cooperative awareness messages. Our next steps would include looking at intersections, and intersections are present kind of two novelties. First of all, there's going to be obstacles such as buildings, construction zones, and trees, which were not present in that ideal highway environment, which we were looking at, even though that was realistic data. And in this case, we want to see if we do get qualitatively different results. And also this right-of-way rules, especially at unsignalized intersection, will have their way in, will dictate the safety conditions that we look at. So they're not going to be just the time to collision anymore. In this case, we carefully have to consider the right-of-way rules of given intersections. What we also want to do is optimize the use of channel resources for awareness of connected vehicles, and that's what this perceived safety framework gives us. So in this case, we're not just limiting the information that we transmit based on other measures, for instance, how much a vehicle moves versus, or how far that vehicle is, but we're limiting this information that we transmit based on how critical that vehicle is to us. And also, finally, we hope to use this to develop, test, and benchmark both perception systems and cooperative perception systems. Thank you very much for listening. Yeah, again, I apologize for the interruption. The internet connection was suffering a little bit, and I would like to take any questions.
Thank you, Sergey, and no problem for that. That happens all the time, which is very sarcastic. It happens even more here in the Silicon Valley than elsewhere. Thank you for the presentation. And I think we have one question or two questions from the chat box. How does the vehicle detection in the side lane happens?
In the side lane?
Yeah, in the side lane. I think you present several scenarios in one of the earlier slides. How does that side lane happens for the vehicle detection?
So I guess we probably mean you mean the on-ramp, or this case?
If you go back to maybe slide, I don't know, 3, 4. I think you categorize different right here. Maybe side swipe safety. I don't know. Side swipe safety.
So yeah, in this case, these are actually independent of detection. Or yeah, in this case, what we look at is which vehicles are critical based on the dynamics of the scenario and the kind of road geometry itself. So if it's a highway and the car is doing highway driving, then these are the safety conditions that we implement. After that, what we do is once we set our safety conditions, which are critical for the scenario, then we say that a vehicle is equipped with a given sensory set. So in this case, this could be, let's say, radars, camera, or LiDAR. And then superimposing those two things, that would give us our perceived safety error, which is how good or how bad the sensory set is doing in this particular scenario in capturing all the vehicles that are critical to us that don't meet those safety conditions.
And maybe I put this question this way: the sensor fusion that you're talking about, what kind of sensors you are using? I mean, or you're assuming, is it radar plus LiDAR plus V2X, or what else?
Oh, in this case, this was camera or radar plus V2X.
So one of the perception plus V2X, right?
Yep.
Okay. Do you have any pointers on measuring channel resources?
Oh, yeah, in terms of papers. So the group at University of Miguel Hernandez has publications where they empirically modeled things like packet delivery ratio and packet sensing ratio that allow you to calculate how much of the channel you're using. That's what we were using in this work, and I would be happy to point you to the specific papers if you ask me.
Yeah. And another question comes from Xinpeng. Very interesting talk. In NGSIM data, error goes to 0 using CPM at 30 penetration rate. Is there a math guarantee on how much penetration needed to achieve no error for all such scenario? It sounds similar to herd immunity.
Yeah, actually, in this case, there for such simulation, even there is no guarantee, because you can make up a scenario where there's two vehicles on the road, and if one of the vehicles is not connected, then pretty much you're on your own at that point to detect that vehicle. So that's the kind of a borderline scenario. Suppose you're all alone on a highway and there's another vehicle that all of a sudden comes up. So this relies on, in this case, you rely on other vehicles and perhaps other infrastructure. So in general, for the scenarios that we have looked at, which are highways for the most part, also other papers looked at kind of more traditional metrics, and they've looked at highways and intersections. 20 to 30% is typically when you see either saturation, or in our case, this perceived safety error going to zero. But again, you can make up corner cases if you're dealing just with vehicles. And then these corner cases could be an argument for having infrastructure, connected infrastructure, because if you have critical intersection where you want to make sure that there's not going to be such corner cases, you might then install some sort of camera that transmits these CPMs. So, but overall, it's 20 to 30%. That's where the benefit is.
And I think some of the audience, they are asking for the papers and the reference link to your paper. So maybe it would be great if you can share just with me so I can post that on our workshop website later.
Great. Yes. Yeah, I have have it down here. And at this point, we have a DOI for the paper, but I can share that link.
And maybe one last quick one from me. If you go back to the animation, whichever animation you're playing for the NGSIM data, I noticed the ratio of the length and width of the vehicle is a little bit weird. Do you intentionally put it this way, or you make some proportional change of that?
Yeah. So in this case, they're disproportional actually, and the goal was, to be honest, to fit them on a slideshow to show 300 meters in length and 3 lanes, such that could be put on half a slide.
Okay.
Yeah, that's so the ratio is weird, but it fits on the PowerPoint.
Okay, I see. Okay. But you use the real data, right?
Yep, this is real data, and furthermore, NGSIM by itself is not that accurate, but for this specific data set, there has been a refinement process that I think a group from Italy went through, where they have eliminated all the behaviors that you wouldn't see from typical car following, and that's actually the data that we are using.
I see.
Yep.
Okay, thank you. I think that the major takeaway that I got from your talk, which is similar to what Hasan just talked about, is the 30%, right? Once the COV penetration or CV penetration reaches 30%, you will see significant improvement.
Right. And one can, also think of this as a trade-off between the two message types. Perhaps at low penetrations to incentivize folks to, get connected vehicles, or incentivize manufacturers to build connected vehicles. The CPM is fairly good because you can have it at those penetrations, at those low penetrations, without saturating the channel. And just one more time, I'm showing the no good region. but after that, perhaps there should be some switching mechanism, or there should be some more sophisticated mechanism in managing this.
Mm-hmm. Okay, great. Thank you. Thank you one more time, Sergey, for a very interesting talk. And that actually concludes our first session of this workshop. Please bear with me one more time. I'm going to share our tomorrow's speakers and tomorrow's schedule. Again, the same time tomorrow, please join us through the Zoom channel. There is going to be another new Zoom link in another invitation, which is tomorrow. And you will see a lot of interesting talk tomorrow. Thank you very much, and see you tomorrow.
Thank you, Zian.
Thank you.